Today's webinar. My name is Beth Capellis, and I'm the Sales and Support Manager here at Triangle Microworks. Thanks for taking the time out and joining us today. Triangle is hosting a free multi-part training series called IEC 62850 Hands-on Training. Today, we are presenting Part 4, Testing in IEC 62850 Systems from Design Simulation to Maintenance. Future training modules will cover topics such as IEC 62850 Engineering Process Basics, top-down versus bottom-up, IEC 62850 Engineering Process Advanced Editions. We'll talk about BAPs and FSDs, ASDs, SSDs, and more. We will have a Part 2 to the testing webinar that we're presenting today, and then we'll be wrapping up with a session on security in IEC 62850. Each training will be followed up with a companion lab exercise to help reinforce the key concepts that we introduce in each training session. We will also provide extended trial licenses to the tools that you'll be seeing in each training to complete the lab exercise. Once complete, you can submit the exercise to Triangle for review and are eligible to receive a certificate of completion. If you'd like to be notified of these future trainings and lab exercises, please answer the survey at the end and to receive notifications. Part 1, 2, and 3 were previously held. If you missed it, no worries. You can find the recording on our website under 62850 Hands-on Training. I'll also drop a link in the chat. You can find the videos and reference documents under handouts in the webinar toolbar as well. So with that said, I'd like to go over some housekeeping items before we actually kick off the training. The training is scheduled to be 90 minutes long. The audience is on mute, so please submit your questions online using the webinar toolbar under the section titled Questions. You can submit questions as soon as you have them. Please don't wait until the end. We will begin answering them online as we have several engineers monitoring the questions and responding to them directly. With that said, I'd like to go ahead and introduce the folks behind the scenes who will be answering your questions. Today, we have with us Jim Coates, President of Triangle Microworks, and Matt Green, Senior Application Engineer at Triangle Microworks. Next, I'd like to introduce our speakers. First, we have Jackson Moore, Digital Substation Specialist at Triangle Microworks. Jackson received Bachelor's of Science degrees in both electrical engineering and computer engineering from North Carolina State University and has a background in power system engineering. Prior to joining Triangle, Jackson spent 5 years as a microgrid system engineer, where he designed and developed load management control systems for multi-source microgrids. Currently, Jackson works with our customers and development team to understand and solve the challenges our clients face. We also have with us Christoph Brunner, President of IT for Power. Christoph is a well-known utility industry professional and 62850 expert for over 40 years of industry experience. Christoph has been involved in the development of the standard since the beginning. He is convener of Working Group 10 and member of Working Group 17, 18, and 19 of IEC TC 57. He is an IEEE Fellow and a member of several IEEE working groups, as well as a member of the PSRC Main Committee and Subcommittee H. So now that you know everyone, I'd like to give you a little bit of background on Triangle Microworks. We were established in 1994 and have over 30 years of communication protocol experience. We are headquartered in Raleigh, North Carolina, and have customers in over 70 countries. We work mostly with equipment manufacturers, electric utilities, and system integrators. The products we offer all support the standard SCADA protocols and fall into 3 categories. First category is source code libraries. We license source code directly to manufacturers for use in their devices and systems. This allows for a much faster time to market and greatly reduces their cost and development time. Licensing a source code library also includes support for your implementation and any issues that may arise in the field. We also provide testing tools supporting these libraries and protocols. These tools are used for communication testing in the lab or the field. They are designed to troubleshoot, simulate, and automate testing for both a single device or a complete substation. Lastly, we also provide a SCADA data gateway supported on both Linux and Windows for protocol translation and data concentration with standard SCADA protocols as well as OPC. It's available as software only or pre-installed on hardware. We are heavily involved in the standard committees that support the SCADA protocols, like UCA Group for 62050 and DMP user and technical committees. Through our participation, we help define the protocols, stay up to date on the changes taking place, and ultimately provide feedback based on our customers' needs as the protocols continue to evolve. So now that you know a little bit more about Triangle, I'd like to go ahead and hand it over to Jackson, who's going to kick off the training. Jackson, I'll go ahead and make you presenter.
All right, thank you, Beth.
Okay, you should have the screen.
All right, so as Beth introduced, the topic of today's webinar will be testing in IEC 61850. We'll take a look at what that looks like through the different stages of the engineering process, and cover in detail some of those areas. And then once we cover the engineering process in our next webinar, or next webinars, then we'll come back and look at some more a detailed view of what testing looks like at some of these different stages. So starting out, here's kind of the general content or outline for today. I'll start out by talking a little bit about the theory of testing and how it applies to those different stages. And then we'll take a deeper look at virtual isolation, kind of learn what that means and what it looks like when you're testing a digital substation. We'll see a demo from Christoph where you'll get to see that kind of visualized in action using some of the testing and simulation tools. Then we'll move into unit testing, so that'll be testing a single device under test. And then finally, after another demo, we'll move into designing to test, how you can think about from the very beginning some of your testing goals and incorporate that into the design process and how that pays dividends in the end. So beginning, what is testing? Well, it's certainly not unique to 61850 or digital substations. Testing is something that we've always needed to do in power systems at large and software development world. Everyone, whatever you're producing, you need to make sure that it actually meets the goals that you set out at the beginning when you started your design. So I guess what I want to drive home here is really this last point. It's not just about it's not just about finding errors. It's about proving correctness, making sure that what you designed behaves as you intended, and making sure that what you intended is ultimately what's going to be a good solution. So again, another concept that is not unique to our industry, it's really true in many, is the idea that finding an error late in your process is comparatively much more expensive, both in terms of time and money to fix, than if you were able to find and correct that error earlier in that process. So, we've got a little picture here on the right-hand side. Basically, if you could imagine these engineers here, if they had made sure that that bridge was going to meet in the middle at the beginning, then it would have led to much less headaches down the line. The same is true in our world as well. So a concept that comes over from the software world, I first heard this concept from one of fellow industry professional, Keith Gray, another convener of Working Group 10. He introduced me to the concept of shift left testing. This is something that I would say I've been pushing, or we at Triangle have been pushing for some time, but maybe not by this name. But I really liked the idea and the kind of the graphical way that it's shown here. So the idea is that traditional testing happens typically at the back end of the project, and it is loaded in that direction, as you can see by the blue triangle on the right-hand side. The idea of shift left testing is to move as much as you can of testing as early as you can in the process, with the idea that, again, you find and correct those errors at the beginning and you don't have issues at the end. 61850 has a set of tools, features, functionalities that enable this and make this easier. So, we'll talk more in future webinars about FSDs and ASDs, but functional specification descriptions, application specification descriptions, you might remember those from our webinar on SCL. These allow us to build small building blocks that we can piece together to make a system specification, and then ultimately instantiate those functionalities into actual IEDs with the the SCD being our description of our entire substation or system. We can begin testing at the very beginning and continue testing throughout the design process. So by the time we actually are out in the field commissioning or doing continuing maintenance, we have a very high certainty that at least our design is sound and solid, our devices are functioning as we expect. So with that in mind, I kind of broke up testing into 5 different stages. The first one being SCD file simulation. This could also just say STL file simulation. As I mentioned, ASDs, FSDs, and SSDs, which are even earlier in the process than the SCD, can all be tested as well and simulated. Next, we would have unit testing. So whereas stage 1 is more about testing our design or our configuration, unit testing is testing an individual device, a single device under test that I might have on a bench. Typically that device would be configured, and I'm making sure that that configured device is behaving as expected. In the factory acceptance testing phase, or FAT, I typically have maybe one bay or a group of devices that work together to perform some coordinated protection, automation, and control functionality, but I often won't have all equipment together and connected via a network at the same time. In that scenario, I might need to simulate devices from other bays in order to test inter-bay functionality. Moving on to commissioning or site acceptance. This is commonly the first time that we have all devices co-located, physically connected, wired up, and available to do a complete system test. At this stage, I no longer need any simulation, and it's all about making sure that my completed and built system is behaving as expected, and it's largely validation. And then finally, 5, maintenance. So once we commission, we get to walk away, but not forever. So maintenance, periodically, maybe a device needs to be replaced or upgraded. In service testing, so periodically, maybe every 1 year, every 5 years, every so often, we need to make sure that our system is still functioning correctly based on rules and regulation in the location that we're at, or even brownfield. So, updating, adding a new bay, so on. Testing requirements change when you're working on a live system. So let's dive in a little bit into stage 1. And this will be covered, like I said at the beginning, in more detail in a future webinar series. I'm sorry, not series, but webinar after we've completed our engineering process, and we're able to see this kind of in action, simulating our design. But in this stage, we are simulating our SCD file, and this is largely about simulating or validating our configuration or our design, depending on exactly where you are in the process. So the SCD file, or system configuration description file, contains all the IEDs that will be in my substation or system. It contains the data models for those IEDs. It documents the communications which will be happening, the signal exchange back and forth between those different IEDs. So within that data model, we certainly have logical nodes. From these logical nodes, they are semantic, as we've spoke about in previous webinars. When I say semantic, I mean that we can infer the functionality of these IEDs based on the logical nodes that are on there. So for example, if I have a PTOC or PTOC, this is a protection logical node that is used for time over current. That's the TOC. So I know that I have a time over current functionality in that particular IED. Taking this SCD file and all of the data contained within it, including that data model, what we can infer from that data model, and the communications that are described in it, we can simulate our entire system in a tool such as DTM, which can input that SCD file and create a simulation of the entire system that acts as, I've tried to coin the term digital cousin. I think digital replica might be the more common industry term, but an approximation of our system that is accurate to the degree that signal exchanges are mirrored, everything communication related is mirrored. And then we can validate that the signal exchanges that we are expecting to occur in order to meet our protection, automation, control goals are in fact happening, and that our system is working as intended. Once we have that up and running, we can take a tool like Test Suite Pro, which doesn't know or care that it's working against a simulation. It just sees 61850 traffic on the wire. It can analyze it and create test scripts to issue controls, publish simulated goose messages, and then validate the outputs that are coming out from my different devices. Outputs being goose messages that are then published changes in sample value streams, reports that are coming out and published to SCADA and the like. So moving over into stage 2, which we call unit testing. So here we are focusing on a single device under test. And Christoph will give us a demonstration of what this type of testing looks like later on in the webinar. In unit testing, we have one configured device sitting on a bench, and then we might have an injection test set also connected to that device. If that device is configured to receive, voltages and currents, maybe it's a merging unit, which will be publishing those voltages and currents out in the form of sample values, or maybe it's we're not using process bus and it's actually a protection device that's wired up directly to CTs or PTs. We can provide those from a relay injection test set, and then use a tool like Test Suite Pro to control that test set, also to monitor communications that are coming out of that device. Next, moving into the factory acceptance testing stage, or FAT. So as I said before, here we might have a group of devices, not a single device, but maybe multiple. Commonly, a single bay might be available on a factory floor where the devices have been configured and wired up, at least in a test configuration. In this scenario, you can easily test communications between the IEDs that you have physically present, and that's typically the level of testing that's done at this stage. If you want to take it a step further, then you could simulate remaining IEDs, maybe devices that exist in other bays, using DTM, using that same simulation that we had in stage 1, and just disabling the IEDs in the simulation that you now have physically present. And then validate the communications that are happening cross-bay. Of course, Test Suite Pro can still be used again to run those tests, to control my injection tests, and then to validate the communications that are coming out of both my real physical IEDs that I have present, as well as those that are simulated in DTM. And in many cases, I can reuse test scripts or test sequences that I wrote in phase 1. We will also be seeing this in action in the second part of this webinar, which will happen after our engineering process webinar. The same is true of our commissioning and site acceptance testing stage. So in this one, all IEDs are present. You'll notice there's no DTMs here. That's because simulation is no longer needed. We have our entire substation physically present, connected, we're on site. Might still need to inject voltages and currents to validate our protection functionality there on site, but a lot of that has already been tested out and vetted either in the factory acceptance testing stage or even the unit testing stage. And then we also have Test Suite Pro present here. So again, the same tests that I configured at the beginning that I ran against my simulation can now be run against those same IEDs. They're just now physical instead of simulated. Validate my signal exchange, make sure that my devices are all functioning correctly, and that the large protection, automation, control functionality that I've designed is actually working correctly. And if it's not, I can test and troubleshoot, visualize those communications, see where the breakdown is occurring. Finally, maintenance and in-service testing. So this is the ongoing testing that happens periodically once our site is commissioned, or sporadically as devices are replaced, or we choose to make an addition to our substation, we add a new bay. So in this stage, depending on kind of which direction you go with it, there's a couple different tools that you have in your tool belt which can come in very handy. Certainly if you're adding a new bay, simulation would come in handy to design and simulate your entire substation, including the new bay, and validate the communications there. But it's also where virtual isolation comes into play. And we'll talk more about this in the coming slides. This is what enables non-disruptive testing. So virtual isolation, kind of the question that virtual isolation seeks to answer is, how does testing change now that signals are being passed over communications and we don't have a dedicated wire for each signal? When we had a dedicated wire for each signal, we could open a fuse, disconnecting maybe a binary signal, on or off that was being passed over a dedicated wire, or where we would typically inject analog voltages. So an injection test set, you might open up a breaker that was leading to a CT or PT, and then using your test switches, input your ejection test set, and then you could test your protection that way, leading to only a single IED without disrupting the protection, automation, and control functionality of your entire substation. Now that the same information is being passed over communications, we need a new method of isolating the piece of equipment that we want to test. So in the digital substation world, kind of depicted here in this diagram, we can see our IEDs here on the right-hand side. These might be merging units or process interface units, PIUs, which are connected to our CTs and PTs and passing information via process bus, so sample values, also goose as well, to different IEDs, which might be making decisions based on that information. So we need a way to be able to pass in test equipment and have it go to maybe just a single device to tell it, a test set of voltages or currents as an example, so that that device can operate its test functionality without disrupting our entire system. The way we do that is virtual isolation. And fundamentally, virtual isolation is a method for testing a live system without disruption or with minimal disruption. As part of that, we have kind of two key concepts broken up into 4 terms that I want to really drive home as part of this section. So the first concept is mode and behavior, those being the 2 key terms. Sometimes you'll see those abbreviated as MOD and BEH or BEH. But no, those stand for mode and behavior. The next key concept is simulation, specifically the simulation flag, which is a flag in a goose message or a sample value message, which can be true or false. And then simulation mode, this is a setting, a controllable setting on IEDs. And I'll explain in the next slides what all of these terms mean and how they work together. Beginning with mode and behavior. So the first thing, before I even tell you exactly what they do, the first thing I want to reiterate is that they're in some ways the same thing. Mode is something that a user sets. Behavior is something that the user reads back. But in most cases, and we'll get into the cases where they don't, but in most cases they will match. So why do we need both? Well, there's always the exception to the rule. They don't always match, and that's because a hierarchy applies. And I've got a nice graphic that hopefully explains what I mean when I say that, but basically we talk about how 62850 is a hierarchical semantic data model, hierarchical being the operative term in this context. I can have a set of mode on a logical device that might be different from the mode on a logical node. And there's kind of a decision tree that decides what the behavior will be when those modes don't match. Now, the important part, what do they actually do? What's the purpose of mode and behavior? Well, they really do 3 key things. The first is determining the quality. Quality is a data attributes that's associated within each logical node or data object specifically. It determines the quality of any messages which are ultimately published. So specifically, it sets the quality to test if I'm in a mode of test. Additionally, when I'm receiving messages, I as an IED, if I'm receiving a message, my behavior or mode will determine what signals I process and use and which ones I ignore based on the quality of those incoming messages. And then finally, if I'm in a mode or behavior of blocked, then it will determine whether or not I block any physical outputs that I might have on my IED. So if my IED is configured to have physical outputs leading to a breaker, I could block those physical outputs so that I will not trip or open the breaker, potentially based on the mode or behavior that my device is in. So what are the modes and behaviors that are out there? Well, there's 5, and you can see that in this table here. And here we really see all the different possibilities for how my device will behave based on its current mode. Let me turn on my pointer here. So if my behavior is off, this is maybe not a typical situation you'll find yourself in, but if you want your device to just stop responding, kind of go into a paused state, then as a result, it will set its quality to invalid. It will ignore any incoming messages, whether their quality is set to test true or test false, and we will not actuate any outputs. If, on the other hand, my mode is in normal, this is the typical state you would find yourself in, my outputs that I'm published, the quality of any goose messages or sample value streams that are coming out of my device, or the data in those sample value streams and goose streams will not have a quality of test. And I will continue to use or subscribe to incoming messages that do not have test set to true, and I will ignore any incoming inputs that do have test set to true. And my outputs will remain unaffected. If I need to actuate an output, I certainly can. Moving forward into test, in this scenario, I will set my quality to test for anything that I'm publishing in the relevant logical node or logical device, of course. And this is kind of a key one here. This is maybe the odd one that people sometimes forget about. If my mode is test or my behavior is test, I will continue to subscribe to, use, process inputs which don't have the test bit set. The big change here is that I will also utilize, process inputs that do have a quality of test. This is the only one where I will use or respect inputs that have a quality of test aside from test block, which I'll speak about here in a moment. Now, my physical outputs do, in this mode, continue to actuate. So if I receive a input with quality test and it tells me to trip my breaker, as an example, based on the internal logic of my IED, I will trip that breaker, or I will actuate my output, which might cause that breaker to be tripped. In contrast, if I am in blocked, not test blocked, but just blocked, then I don't make any changes to my quality. At this time, there is not a blocked quality, although that might change in the future based on addition to the standard. I do continue to use inputs which do not have the test flag set and ignore those which do have it set. However, the key difference here, what blocked means, is that I do not actuate my outputs. At this point, you've probably figured out what test block means. In some ways, it's a combination of both test and blocked. I set my quality to test. I continue to use both normal inputs and those which have quality of test. And I do not operate my outputs, again, because of the blocked. In order to see what this looks like, and we'll get to see this again in a moment when Christoph shows us the demo, but here, if you could imagine this being a visualization of communications that are happening between two different IEDs, this particular IED here on the left-hand side is publishing a goose message that has a normal quality. The test bit is not set. And that is in fact processed by all four of these devices, regardless of what their mode or behavior is in. Now, of course, those are in blocked, will not actuate outputs, but they still will receive the input that's coming from this device and process it up to the point where the physical output is actually changing. In contrast here, if my publishing device, the device here on this left-hand side, is in mode test, then that will be reflected in the goose messages, or as long as I've included quality in my data sets. I'll speak about that a little bit more at the end, but then the test will be reflected in those goose messages, which are then published out and subscribed to by this IED in these four different logical nodes. Now, these four different logical nodes are in four different states or have four different behaviors. Those that are in on or just blocked would ignore that message with quality test, while as those with test or test blocked would process this message. Now, what happens when they don't match? As I said before, it's a little bit more complicated than mode and behavior always matching, and that's because of the hierarchy that I spoke about before. So as an example, if I set my logical device to off, a logical device being the parent, logical node being the child, regardless of the state of my logical node, I guess that would actually be the bottom row in each of these four. If the parent is off, then the child is always off regardless. For other states, for example, if the logical device is in test, that again is inherited to the device, to the child. and the behavior of the child would still be test. On the other hand, if the parent is in on, but the child is in test, then test actually wins and the behavior of my child would be in test. So this table, which we'll put into the cheat sheet that will be distributed later on with the companion exercises, just kind of shows you who wins when the mode of the parent logical device and the child logical node don't match up. Next, the other kind of key concept that makes up virtual isolation is simulation. And this isn't simulation like I spoke about before, where I'm talking about simulating whole devices in DTM. This is different. This is a term that's specific to communications in 62850, and there's two parts to it. There's the simulation flag, which is something that comes out from a publisher, and there's this sim mode, which is something that you set on a subscriber. Now, of course, one device can be both a publisher and a subscriber, but the sim flag really is only relevant not on a real IED, but on a digital test set. So a device which is strictly used for communication purposes. A real physical IED would never have this simulation flag set to true in a goose message or sample value message that it's publishing. On the other hand, all real devices would take advantage of simulation mode. So each IED that you might have will have a logical node named LPHD. This describes the physical device. You might see nameplate information or other information about that physical IED. In it is a data object called sim. A lot of times it's referred to as lphd.sim. So setting lphd sim.stval, specifically that's the data attribute, to true is how you configure this device to subscribe to simulated messages, messages that we know are coming from some sort of piece of testing equipment. So again, these simulated messages are going to become from a digital test set, for example, Test Suite Pro or another tool like it. They are identical to real messages that are coming from actual IDs, which might also be on the network, except for the critical piece of information that there's a flag in the header, which I'm calling the sim flag. It's a simulation bit in the header of the message. You could view it if you were to capture that message on Wireshark. That flag is set to true. This critical distinction between those two messages, along with the ability to set a subscriber's LPH sim mode to true, is what allows us to subscribe to simulated messages to test functionality on one particular device without disrupting the rest of our substation. I should go one step further. Because of the latching behavior that I'll discuss on my next slide, this is really a per stream level of control that we have. If my device is subscribed to 10 goose messages, yes, I only have one LPHD sim for my entire device, but I need only simulate one goose stream. That device will, the subscribing device, which has LPHD sim set to true, will process that simulated goose stream as well as any other streams which it might be subscribed to, which are coming from real devices which don't have the sim flag set. So, as I alluded to a moment ago, there is a latching behavior. There's always a little bit of a gotcha, and I want to make sure that I explain this key concept here. So, let's say I go in to my substation and I set LPHD sim to true on a particular device. That device will continue to process and use streams from the real device, the real publishers, which don't have the sim flag set, until the point at which it sees a simulated stream. And then that particular stream will be latched onto, if you will, and the real stream coming from the physical IED will be ignored from that point forward until LPHD sim is set back to false. I'm going to repeat that again because I think it's a pretty important concept. So I go in, I take one particular device, I set its LPHD sim to true. That device will continue to process streams which do not have the sim flag set. and then for each of those streams, if it suddenly sees a simulated stream which replaces the real one, it will begin to ignore the real one and process the simulated one forever, even if that simulated stream goes away, until the point at which I set my LPHD sim back to false. So it's very important that when you're done with virtual isolation testing, you take all of your devices out of simulation mode, setting LPHD sim back to false. All of this works together to ensure clear separation between the simulated data and the real data streams. So now a chance to see what some of this looks like in action. And again, in a moment, we'll get to see this demonstrated by Christoph. But here on the left-hand side, I have a publisher, and then I have two subscribers on the right-hand side, indicated here by BCU1 and BCU2, these being two different IEDs. Now, you'll notice that the LPHD sim is set to true on BCU2. Notice that this is at the top of the device and it's not on the logical node. Whereas mode and behavior can apply to logical devices and logical nodes, LPHD sim is for the entire device. And notice that even though LPHD sim is true, my devices continue to process messages which are coming from the real device, in this case, the BBP over here on the left-hand side. And that is because these devices over here on the right have not yet seen a simulated stream. Now, in this example, I now am publishing a goose message from, in this case, from Test Suite Pro, which has the sim flag set. My subscriber over here on the right-hand side, which has LPHD sim set to true, meaning it's now configured to subscribe to simulated goose streams. We now see an X over the inputs coming from my real device, because this device should now be processing the simulated goose stream and using that instead. And critically, as I mentioned before, if I was to stop publishing this goose stream, if I left my LPHD sim to true, then my device would not go back to receiving or processing the real goose stream. It would ignore it, and I would need to set LPHD sim back to false in order to process those simulated, those real messages. Now, lastly, before we move over to our demo, I just want to talk a little bit about LGOS. So you might remember LGOS from some of our previous webinars. LGOS is a logical node that gives us the subscription status of any goose messages which my device is subscribed to. Its brother LSBS does the same thing, but for sampled values. So a lot of times when we talk about LGOS, we're just talking about it as a tool to let me know if my IED is receiving the messages that it's supposed to, the goose or sample value messages in the case of LSBS. But it does have another functionality that's specific to the virtual isolation. That is, aside from just telling me if I am subscribed to a goose or sample value message, it can also tell me if the one that I'm subscribed to is in fact simulated. That can become very important if I'm utilizing virtual isolation. I can know for certain that my device under test is no longer listening to the quote-unquote real goose or sample value stream, but instead, based on its LPHD sim status and the ability to see a goose or sample value message which has the sim flag set, I can see that it has latched on to that simulated message. I hope this is clear, and Christoph will now get to demonstrate some of these concepts a little bit more clearly, maybe we'll see, with DTM and Test Suite Pro. I always feel like being able to see these in action, being able to visualize some of these can really drive home some of these concepts. So with that, I'll go ahead and turn it back over to Beth and Christoph.
Okay, thanks, Jackson. Let me go ahead and make Christoph presenter. Okay, Christoph, you should have the screen. You're still on mute.
Welcome everybody. Can you hear me and can you see the screen?
Yes.
Okay. So welcome everybody. After Jackson's introduction, I wanted to show you now a little bit how this looks in reality. What we have here, we have created a little workspace where we simulate a couple of devices to illustrate the different situations. So what you see here on the screen is the signal flow diagram from Test 3 Pro, and we basically have three main devices in here. We have a busbar protection that we assume that sends out a trip, and then you have a bunch of brake control units, two of them, and in each of them we have four logical nodes for circuit breakers, and we just want to illustrate a little bit how the reaction is when you receive a trip from the busbar protection, and the different logical nodes here are in different modes. So what you see here, basically, the first logical node in the VCU is in mode on currently. The second one is in mode blocked. The third one is in mode test, and the fourth one is in test blocked. You have the same situation as well in VCU2. The only difference is that VCU2 currently has LPHD sim set to true. That means it's looking out if there is somewhere a simulated message available that looks like the same message sent here, but with the sim flag set. Currently it's not, that's why it's still listening to this message. Initially we have all the breakers here, they are now closed. The whole application behind, we are simulating in our distributed test manager. What we see here, the window, how we can control it. So the distributed test manager is simulating on one side the busbar protection that sends out a trip. We can activate that by selecting here fault, and then it will send out a trip. We can here select the mode that our busbar protection is in. So currently it's in mode on. And then here we can visualize the goose reception for those two devices. So now the status for both of them is true. They receive them, but nobody has switched to the simulated message because there is no simulated message on the wire. And what we can show here, we can visualize the signal operate OK that has been introduced. So basically, when a function receives something to operate, it will activate this operate OK bit for a certain time. And that it will be doing independent if the output is blocked or not. So that can be used to verify the behavior, but without sending a trip. So in principle, we can verify that the op OK would go to true when it receives a trip, but as it is blocked, the output should not change, so the position should not change. So that's why we have this operate OK, and we are able to visualize that here as well. Okay, so now let's do a first test. And the first test, we will send a trip from the busbar protection. The mode is on. So now what can we expect to open? We can expect that this breaker will open because the mode is on. This one will not open because it's blocked. This one will open, it's in test, but as Jackson has mentioned, when we are in test, we still also respond to signals coming from a device that is not in test. This one again will not open because it is as well in blocked. So let's go to the custom display and let's do a fault here. I activate the fault. We see here the trip is active, and we see the first two breakers and the third breakers, they both have opened. The other breakers remained closed, so exactly as we expected it. We can do a reset here. And we close. I will repeat it again, and now you should also observe here. You should basically see the op OK getting shortly true for all of them. You may not be able to see that over the web, but then for the ones that will not operate, they stay a little bit longer true because it's trying to operate and is waiting until the timeout expires. If I do the fault again, you see those, it did an operate OK, but it doesn't operate. It has an operate timeout, and after a certain while, those will go away. So now they have gone away, so it abandoned the operate. It was just not successful because, in fact, the trip didn't go, the signal didn't go out to the switch. Now, next one I want to show you is that we are not faking that. So if I go back to the signal flow, we have a way to change our mode behavior here. I go to the mode behavior, and now I will set this mode into on. I can change that here, change mode. I set it from blocked to on. You can do that from remote. It sends the signal down to the simulation. And after a while, you see now it indicates the mode is on. So if we do now the same trick as before, what we should see is that this switch will also open because its mode is now on and not blocked anymore. So let's do that. We activate the fault, and effectively, yes, we see that switch has opened as well because it's now not in blocked mode. And we can reset it, and we can go back to our signal flow, and we will set this back again to blocked as it was initially. I can change that mode back to blocked, can do an operate on it, and after a while we see it's now switched back to blocked. Okay, so that was the first test. Now let's see the operation when this device would be in test mode. So you want to test a couple of devices or lots of functions, but not necessarily everything should operate. So that's why we now put this as well in test mode. And you can do that down here. You can put this in mode test here. You see also here, it indicates now that this is in test. On signal flow, where you see all the signals, you see the quality now is test. It's still good, so it's valid, but it has the test quality bit in addition set. So it's test. And what you also see in the visualization now, this visualization already evaluates what would happen in order to show you. So you see here a cross, which basically indicates as the signal should not be received by this logical node because the behavior is on, but the quality of the signal is getting in is test, so it should not be received by this logical node. It should also not be received by this one. However, it should be received by those, and the same on the VCU2. And I can zoom a little bit in so that we see now more the upper part. So, yeah. Okay, so that means now if I operate here, what we will see, we will only see the third breaker open in both cases. The other ones should stay closed. So let's do that. Let's again create the trip. And we see this one have op OK, those one don't have op OK, this one have op OK, but they don't operate because it's blocked. These ones have operated. We see here those two switches have operated. So everything so far worked as expected. Now we can reset that, and now we will look at the simulation mode. As we have said, we have here the low VCU has the LPHD sync flag set to true, what we also see here. But currently there is no simulated message available. That's why it's still receiving the normal messages. This one not, because it is in test. We can change that back to normal. So now it will receive it again. And just to verify, you can do a trip again. And if we go to the custom display, we see they have tripped again, like it was before when we were normal, and we can do a reset. Okay, but now let's add a simulated message. For that, we can use our Goose Publisher in our Test Suite Pro tool, where we can send out messages that are configured in the file. By default, we have here the simulate flag activated so that they will not interfere with the messages from the real devices. And what we want to simulate is this message from the bus bar protection. So we can go here. And initially we want to have a trip general fault. We want to do it, initially we can do it as a normal one. So we set our quality just to good, no test flag. And now we can start publishing this message by clicking here. So now we are publishing this message. And what we see over here now in the signal flow diagram, we see now there is a simulated message available. So we can put that here as well. We can visualize. And now when we zoom into the details here, you see now it shows that it will not receive the normal reception message anymore, but it will now receive the simulated message down here that is coming from our test report that is publishing this as a test equipment. So now if we are sending out a trip from this message, the quality is good. What we should see is that basically the first breaker and the third breaker should open because the quality is good. Those one will still not open because it's blocked. So we can change here the value to true, and we can go to the custom display to see it happen there. I can republish now this message that will initiate a change of the whose state number because the value has changed. I can republish that, and we see indeed in our device that receives the simulated messages, which is VCU2, the first and the third breaker have opened. The other device, nothing has operated because that was the simulated message, and the other device is reacting on the non-simulated message. I can take this back again, republish. The trip is gone, but the breaker is open. And we go back to our DTEM application, do the reset, which will basically close the breakers again. Now while we have publishing the simulated message, we can see if the normal message still works on VCU1. I can now also create the fault from VCU1, and we see VCU1 still reacts on the normal message, but not VCU2, which is now looking at the simulated message. And I can again reset. And as a last test, we can now also here emulate a device in test. So now when we republish this, okay, first of all, we just republish it with the quality test, and we can go to the visualization here. So it now should say that this one will also not receive the simulated anymore. So if I republish, now you see it has decided, yes, that will not be received here. It will still be received on this one, however. And let's see if that's true. So now we send here again the value true. We republish the message. So now we are sending a trip from the simulated device. We republish, you see the state number has increased, and indeed this breaker has opened because he is in mode test. This one would have had received it, but he is in test blocked, so he didn't operate. Okay, so now that we are done with our testing, we can stop publishing our simulated message. So we are stopping to publish that. And you see after a while, so there is no published message anymore. So we have the dashes here showing that there is no message coming. But what happens now if I do a trip from my normal device? What should happen is those still don't open, because remember, as Jackson mentioned, there is a latch. So once we have been in simulated mode, we will not go back and listen to the other ones until somebody tells us that we are not listening to simulated mode anymore. So if I now create a fault from this device, the VCU2 will still not operate. Before we do that, we need to do a reset so that everything is reset. And now we can do a fault from here, and we see VCU1 operates, but VCU2 did not operate because VCU2 is still expecting the simulated message. To change that, we can go back in our mod behavior tool, and now we can tell the VCU2 that we change the LPHT sim and we want to set it to false. That means it should not be simulated anymore. We send an operate. And after a while, you see now it's back to normal. And if I do again from my, it's also indicating it will receive these signals. If I go back to our real device and send it, first let's do a reset so that all breakers are closed again. If I send a trip now, we have the situation that all breakers open that are not in blocked mode. So as we started, and the other ones would open, but they are blocked, so we have seen the OK. And with that, I think I will hand back to Beth.
Okay, thanks, Christoph. With that, we're going to just take a couple of minutes to do some questions. So let me start with the first one. This is just a point they're asking for clarification on. And I'll open this up to both Jackson and Christoph. When a subscriber with lphd.sim is set to true and is subscribed to multiple streams, does the latching behavior of ignoring streams without the simulation bit set only apply to that specific stream, or does it apply to all subscribed streams?
Should I take that?
Yeah, go ahead.
So the latching behavior is, I mean, the switch is only happening for messages where there is a simulated message. As you have seen, when I started the demo, there was no simulated message. So it didn't switch over and it still received the normal messages. So if a device is subscribed, let's say, to 3 goose messages and 1 sample value message, and at a certain moment for one of the goose message, a simulated one is available, it will still continue to listen to the other ones that where no simulated message is available. So it only switches the reception of that stream to the simulated where there is one available. So obviously that also then applies to the latching. So because it never latched to something else on the other ones. So it's only when the simulated message goes away, the one that it now switched, it will not receive the normal one, but the other ones, it will continue to receive the normal one. I hope that was clear.
Yeah, it is per stream.
Okay. Next one, I think this will be for you, Jackson. You might have a slide, so I can switch back to presenter for you to show, but let me go ahead and ask the question. Could you please explain the roles of the test bit and the quality attribute in the simulation flag?
Sure.
I did make you presenter again if you wanted to refer back to a slide.
Sure. So, I mean, these are the 2 key concepts of virtual isolation. So let's start with mode and behavior. Mode and behavior, based on how it's set, influences the quality. So in this case, that's what we're calling the test bit of any messages that you're outputting. So in this example, this logical node is set to behavior or mode of test. Therefore, the quality of anything that's published, any data attribute that's contained within a logical node that's put into a goose message will carry forward that quality of test. That's what we see reflected here by the word test. And then over here on the right-hand side, these are 4 different subscribing logical nodes that are in 4 different modes or behaviors. We see that the one that's in on, we see an X here indicating that he's ignoring that because it has quality test. This one's in blocked. He's also ignoring it because it's quality test. But the 2 that are in test and test blocked receive it because it has quality or the test bit is set. The test bit, quality test, same thing in this context. So that is test bit, that's mode and behavior in a nutshell. As for simulation, I'm going to jump forward to this slide. So in this case, the entire device is in simulation mode. That just means that we have set LPHD sim to true. That means that all devices, all subscriptions on that IED, if they see a simulated simulated version of the goose or sample value message, they will use that instead of the real one. Now, these are two distinct concepts. Simulation, which includes the sim flag, which is a flag that is in the header of the message, and LPHD sim. That's a distinct concept from mode and behavior, but they can certainly be used in conjunction, and they commonly are. It's just that they don't have to be in their two distinct concepts. So I hope that explains or reinforces the distinction between the two.
Okay, thanks, Jackson. I'm going to do one more question, and then we'll cut back over to the presentation. Last question: does the OK only go high in the blocked or test block mode? I'll open that up maybe to Christoph. Jackson, feel free if you want to jump in.
Yeah, Christoph, I believe op OK always goes high when, regardless of whether or not you're in normal or test or test.
Correct. I was just answering that question. Yes, correct, because that's exactly the purpose why we introduced op OK, that we can observe if a test would be successful without really having the braided tripping. Let's assume you want to do a protection trip from a relay, including so you want to know the performance, but you don't really want to trip, but you still want to know if it would have tripped. That's exactly what we can use. So you don't need to physically remove the wire, how we would do in a traditional environment. You can lead the wire to the trip coil there. You can do the whole test, and the OK has also a timestamp, and then you can use it to measure the performance of the trip without that the trip really would have happened. So that was exactly the purpose why we introduced op OK. So yes, it goes always through independent of the mode we are in.
Okay. All right. Well, thanks for answering those questions. Jackson, you have the screen if you want to continue on with your next set of slides.
Sure. So now we're going to talk about unit testing. So, as I spoke about at the beginning, unit testing is a single device under test, or you'll see the acronym DUT throughout my presentation that we're working on. And it doesn't have to be configured in the case that we'll be discussing. We're going to be assuming that it is configured. Potentially, you could also be performing unit testing on a device that just comes from the manufacturer with some sort of default setting. But in this case, let's assume we have a configured device, and we want to make sure that that single device by itself is doing what it's supposed to be doing. And that might involve a lot of testing that is outside of 62850, but we're specifically talking about 62850 unit testing. So I broke that up into kind of 4 general steps. This is something that we performed at the IOP last year on a handful of devices. We performed unit testing before we began functional testing. And so that's kind of where I got this layout from. And I'll walk through it. So beginning by validating the configuration, confirming the subscription, so goosing sample values that this device is supposed to subscribe to. Functional testing, this is, again, where the fact that this device is configured becomes very important, because we need to make sure that it behaves correctly based on the configuration that we've given it. And this includes its ability to publish goose or sample values correctly. And then finally, confirming virtual isolation. This is just making sure that the device supports virtual isolation and that it's correctly configured and working the way we expect. So walking through these in a little bit more detail, beginning with validating the configuration. So when we have a configuration, this might be the form of an SCD file, which describes the capabilities of all of our devices, or it might be a CID file, almost like an extraction from that SCD in some ways, that contains all the configuration information for a single device. In either case, that is ultimately pushed down onto an IED, along with maybe some other settings that are vendor specific. And then that is what configures that particular IED. Now we can load that SCL file, be it an SCD, an IID, a CID, into a tool such as Test Suite Pro, and it can perform a discovery of that device and then validate what it discovers from the device against the SCL file that we provided it. In theory, this should be a one-to-one match because the same SCL file that I loaded into the tool, Test Suite Pro in this case, should match the SCL file that was used to configure that device, but this is just a sanity check to make sure that they do in fact match. Model compare is the name of the feature in Test Suite Pro that allows this, but what it's doing in the background is a discovery. Discovery is a feature within 62850 where a client can reach out to a server and ask for the server to describe itself, describe its own data model, and then model compare is comparing the results of that discovery against what's defined in the SCL file. Next part of validating configuration would be making sure that that device is in fact publishing what it's supposed to publish. So that could be Goose, that could be sample values. Maybe it could also be validating the reports as well that will ultimately be used by a SCADA or pass through a gateway to some remote SCADA system. This is where the Goose tracker or the sample value tracker would come in handy for validating that the expected Goose messages and sample value messages are on the wire. Again, it's more than just making sure they're on the wire though, because Test Suite Pro can use the SCL file. It defines not just that there is a Goose message there and maybe what the name of the Goose control block is, but it also tells you information about what data should be in the data set. As an example, that information can be compared, what's defined in the file, again, with what's discovered on the wire, and it serves as a sanity check to make sure that your device is configured the way you were expecting. From there, now that we know that our device is configured with the right file and that it's publishing, now we want to check its ability to subscribe. So there's a couple of different ways you could do this. You could get another real IED on the table that's configured to publish the Goose or sample value streams that your device under test is configured to subscribe to. You could simulate the entire devices that are publishing in DTM or Test Suite Pro, or you could simulate just the relevant streams using basically a 62850 test set. So in this case, a tool like Test Suite Pro, or others, in order to simulate the Goose streams, the sample value streams that device under test is configured to subscribe to. Now, simulate is a little bit of an overloaded term here. You may or may not actually have LPHD sim set on your device at this stage. You may or may not have your digital test set configured to publish Goose and sample value streams with the simulation flag set. In either case, you're just looking to make sure that your subscribing device can actually receive those messages, and the way that you tell that it can is via the LGOS or LSVS attribute on the device, as I spoke about before. So once I begin publishing those Goose streams, I should see LGOS update on the subscribing device. Now that we've confirmed our configuration, our ability to publish, and our ability to subscribe, we are ready to begin functional testing. So this is where we really want to make sure that the device behaves in the way that we expect as part of some larger scheme. So now we might begin to, aside from just having our Goose and sample value streams published, we might also need to hook up an actual injection test set to publish real voltages and currents if necessary, if that device is going to be hooked up to CTs or PTs once it's installed. And then once we have all of that in place, then we begin to manipulate the Goose that the device under test is subscribed to, the sample value streams, currents, and the voltages, all of the inputs effectively that are coming into that device. And then we're monitoring the outputs. So when I say outputs, those could be physical outputs. It could also be Goose messages that the device under test is publishing, sample value streams, or even just reports that are coming out of the device. And you might want to create test scripts. You don't need to do this all by hand. If you're going to be doing it repeatedly, then it might be useful to kind of put together a sequence that manipulates these things in order in a tool like Test Suite Pro. And then lastly, Virtual isolation. So we're not going to truly try and virtually isolate the device. We just don't need to because there's only a single device sitting on a bench at this stage. But we want to make sure that virtual isolation is supported and that it works as intended before we get into a situation where we need it. So just making sure that mod or mode is controllable, making sure that the behavior updates as we expect once we issue a control to the mode. Make sure that the lphd.sim bit is controllable and that we can write that to true. And when we do, make sure that the device is able to subscribe to simulated streams and that LGOS and LSPS are updated accordingly. So that's a quick high-level overview of what types of testing we want to do as part of unit testing and a little bit about how those can be accomplished with Test Suite Pro. Now I'm going to turn it back over to Christoph for our second demonstration where he will be showing some of this in action. Christoph, go ahead.
Okay, Christoph, just made you presenter.
Okay, can you hear me?
Yes.
I'm just changing now to share my screen, and I think that's the one. Okay, Jackson, if you make your loudspeaker a little bit lower. Okay. Before we start with the unit testing demo, I wanted to show you a quick introduction on what is our system setup. So basically, what we assume as the future system is a substation with an incoming feeder and a couple of outgoing feeders. In each of these bays, we have basically a standalone merging unit, and we have a bay control and protection unit, basically a feeder protection. What we are using here in our demo is devices from Schneider, the P7 series. We have a merging unit and we have a protection. So this little system that we see here is also what we will use in the next webinar about engineering to develop our system, and then we will also use it in the webinar testing part 2 when we talk about system testing. Then we will have the complete system there. Today we focus on one bay and in particular on one device that we want to do unit testing. So the bay is visualized here. We have basically our protection device, which is the Schneider P7 feeder protection. We have a merging unit, which is the Schneider P7 merging unit. We have goose messages going on between the devices. On one side, the merging unit is also an interface to the breaker. So we see there's also the logical node XCVR in. And as such, it's sending a goose message with the breaker position to the BCPU. On the other side, the BCPU itself, which has the control functionality in, besides the protection, it sends also the operate open and operate close signals down to the merging unit when a control request is performed. And of course, if a fault happens, it will send down the trip to the merging unit. So what we're now focusing is on the unit testing of this BCPU. So we have here basically the setup. We will start the test with a Test Suite Pro as a test client. We will first verify the presence of the published messages. We will verify the subscription to messages. Like Jackson has mentioned, we can check LGOS. We can also see if it reacts to subscriptions. So that will be done with Test Suite Pro only. But then in the next step, we want to do some basic functional verification. And in that case, we need to have something that simulates our breaker. And we are using DTM in that context to simulate basically the interface to the breaker and the breaker operation itself. So we'll do a small test there, just trying to operate the breaker and see that it performs correctly. And last but not least, we also want to do a virtual isolation test. So basically, we'll set the BCPU in test mode and issue control requests with test activated, and we should then observe that it will not react because the goose message with the CSWI or open or close should have the test bit set there. And as long as our simulation in DTM is not set to test, it should not react. That means the operation should not work. So that's what we want to demonstrate. And now let's get to Test Suite Pro. So starting with the first thing, verifying the messages. So Test Suite Pro has basically been loaded with the SCL file of that complete feeder. So the file has both the merging unit in as well as the BCPU. And if you look now at Goose Tracker, what we see is that the BCPU is sending the signal, but the merging unit is not present as we are doing a unit test, so this Goose message is not there. Currently, no Goose message is sent out. That's also why we see the breaker position here that is reported from the protection unit. We see that as invalid. That's why it's yellow here. And if you go to the LGOS, we also see that it says it should receive a message from the standalone merging unit, but the red, it says it's not present, it doesn't receive a message. But the message that are sent by the device, so the Goose message we have seen, it is here. We can also go to our Goose viewer. So we basically see there is a Goose message sent out. For the moment, nothing changes, but there is a Goose message sent out. We can also go to the report viewer. We see there is reports present. So reports have been sent by the device. And as soon as we now will try to do some action, we can also see that additional reports are sent. So I will now go back here to the custom display. And now, as a test tool, I try to simulate the message from the sample from the merging unit. In this case, I don't need the simulation flag because I really want to behave as the real standalone merging unit that is not present. If I go to our Goose publisher, I have deactivated the bits that would tell it from a simulation device. So now it looks really like I would be the merging unit. I have the position set on, quality is good, no test. So if I now activate this sending, the CSWI should change here and should become the position on. I start publishing now. And you see the position is now on, which is indicated through the red. We could control it to open, but that is nothing simulated, that would not work. But if we go back to the report viewer, we see now we have also have a new report. And if we click on the details of that, we see the latest report says the status value is on, quality is all good. If you looked at the previous one, there was a quality bad, invalid, because there was no input received on the Goose message. So that was before we have activated the Goose message. And it was also indicated intermediate state, which is basically what the systems typically do when they don't get a position of the switch. Now, if I reactivate that, if I resend now the position off, we should see a new report getting in. And that happened, and the new report now tells us the position is off. And we didn't see any Goose messages because the Goose message would only be if we operate. Okay, so that so far worked fine, but now we want to do some functional testing. In order to be able to do that, we need to have a simulation of the behavior of the standalone merging unit. And for that, I will use Test Suite Pro. That means I need to stop publishing the Goose message. And you see immediately the BCPU has detected there's no Goose message anymore. LGOS again shows there is no Goose message. And now I have DTM running with a little simulation of just the breaker interface and the breaker. I need to enable that. That may take some time. You should see as soon as it receives the Goose message, it should change. It worked before. Okay, now we see it receives a goose message. The simulation is not yet running. That is shown as unknown. We will now start of the breaker. So now we see the position is open, and we also see here the LGOS has shown it receives a goose message. Now I should be able to do an operation here, and then we should see the goose message going out with the operate open, and the simulation should react and should get the position back that it's closed. Let's do that. The system asks me that I will operate the switch. Are you sure I want to do that? Yes, I want to do it. And we see the switch has opened. You may have heard a little click from the relay, probably not. If we go to the goose viewer, we now see there was goose message sent down. There was the first goose message. I can select both goose messages. And then we will see in the first goose message, operate open went to true. And when the switch had operated, operate open went back to false. So that's basically interaction between the vCPU and the switch that works. So I can redo and operate. And then now back to close. So we should then see operate close become true. So let's go back to the display. Let's initiate a close request down. And again, it closed. The switch is now closed. And if I go to our goose viewer, we now have two new goose messages. And as expected, now we had the op close that first went to true, and then it went back to false. So we could prove also that apparently it's not only correctly configure the device, but it's also the basic functionality is working. Now, the last thing I want to do is to see if the test mode behaves. And for that, I want to set the device into test mode. I go into my mode behavior, and the functionality in this device we have multiple logic devices. It's the Bay LD that has the logical nodes in for the control as well. And this is controllable here, so I can change the mode here to test. Can do an operate. And after a while, it shows here now it's in mode test. So now if I do again an open, it should fail because it will send out the goose message with quality set to test. And our simulation of the standalone merging unit should not react. So let's try that. I do an open. And it's waiting, and it doesn't get the result back. And what we see here down in our output window, we see we got an error message back, which is basically saying blocked by mode. So it didn't go out. And if we look at our goose viewer, we should see now the two goose messages. We see here the quality here is set to test, and that's why the DTM did not react. And with that, that's the end of my little demo, and I hand back to Bess or to Jackson, whoever.
Thanks, Christoph. Yep, I'll make Jackson presenter. He's going to wrap up the training for us.
Excellent. All right, so I'm going to end today with a soapbox that you guys might have heard me speak about before. It's something that is near and dear to my heart, and that is designing to test. So the goal here is to instruct everyone about, some of the best practices, things that you can do that are in your control when you're designing a system, whether it's top down or bottom up, that will pay dividends down the line when it comes time to test and validate. These fall into a couple different camps of things that you can do. So I'll talk about reporting, best practices there, Goose, data modeling, and finally the substation section. So beginning with reporting. So first, when I'm talking about designing to be tested, and specifically in the context of reporting, it begins with including your clients in the SCD file. So typically when we include clients in an SCD file, we're talking about SCADA systems, right? So maybe your gateway or a local HMI, but also your testing client. Typically, testing tools fall in the category of client, even though they might be subscribing to Goose or even in some cases publishing during testing scenarios. But in 62050 terms, something like Test Suite Pro or similar tools would be classified as a client. That means that you can create or ask that vendor for an ICD file, which describes the capabilities of that device, and then include it into your SCD file, your system configuration description. Once you do that, you are able to allocate report control blocks specifically for that client. So that might go so far as to actually reserve specific control blocks for that client, meaning that other clients out there, like maybe your HMI or your gateway, will not be able to grab those clients and, those report control blocks and use them for themselves. You don't want to get into a situation where you're trying to test. You need some data that's maybe not available via Goose, but is available via a report, and those reports aren't available because they're already all being used up by other clients. With that said, it's not always the case that the data that is included in the report control blocks that are being passed up to SCADA is the same data that you need for testing. So consider creating data sets specifically for your client and associating them with a dedicated report control block. So just examples of the types of data that you might need is certainly quality and timestamp are very important when you're testing. You want to know exactly when data, when it changed. We talked about op-OK earlier. If an output was blocked, maybe you'd want to include op-OK specifically for testing and put that into a data set and then reserve that data set for a client, a testing tool. A lot of this same stuff can be applied to Goose as well. The big difference there is that Goose is multicast. You don't worry about someone else grabbing your Goose control blocks, but there are other considerations that need to be taken into account. One of them would be with networking. So as an example, you might be using VLAN IDs or MAC address filtering. If you do create your client and you actually configure your client to have XREST for these Goose messages, then if you're doing a network configuration automatically based on your SCD file, those Goose messages would be routed to that client. You won't be moving your testing tool around to different points on the network in order to capture the data that you need. It can all be funneled by the switches to the point where you're planning to connect your testing device. Additionally, you can consider creating custom Goose control blocks that are specifically used for testing. If you have data that you need high speed via Goose that's not already in an existing Goose control block, if you don't want those Goose messages on your network after the fact, then you can disable a Goose control block when it is not in use and it will no longer be publishing. As always, please include quality. Virtual isolation relies on the quality being included in your Goose messages, not just the status values, but also the quality so that you can see if that test bit is set. Next, a little bit about data modeling. So this falls into two parts, but it both revolves around the idea that you need to take advantage of the tools that the standard gives you. So LGOS and LSVS exist. Most major manufacturers support them at this point. It might be up to you as someone who's configuring this SCD file to actually utilize them if it's not done automatically by your system configuration tools. So please take advantage of them. That is the only way for you to know for certain that a device is actually receiving the Goose message that it is configured to subscribe to. Even if you see it on the network, it's possible that if you're using filtering or VLANs, that it's not getting to the intended device. Whereas LGOS or LSVS give you confidence that it is actually being received and processed by the subscribing device. It also becomes very important if you're using virtual isolation to know whether or not that device is receiving the simulated stream. There are other diagnostic logical nodes as well that you can take advantage of, other tools in your toolbox that are part of the 62850 standard. So these would be LTMS as an example that can give you insight into time synchronization, knowing who you're synchronized to as an example, and LCCH, which gives you information about physical network ports on your device. This can become especially important if you have an HSR or PRP ring topology, a redundant network, and you can see which ports are in use, which ones aren't enabled, and the like. And then lastly, utilize the semantic model that is described in 62850. That's not to say that you should never use GGIOs, but there are over 200 different logical nodes that are defined as part of the standard. It's very unlikely that you'll need all of them, but it is very likely that the data that you need to describe or transmit is available in one of those different logical nodes, in one of the different data objects on one of those logical nodes, and one of the different data attributes. So I'm not saying that you should never use GGIOs or that they have no place. GGIOs are generic logical nodes that can contain whatever data you want, but there's no semantic way to know what data that is contained within that GGIO. I have to have some external documentation to know that a specific GGIO is a breaker status, as an example. Whereas if I included that in an xcbr.pos.stval data attribute, then I would know that it's actually a breaker status. This can be very useful in testing, but also in other areas as well. It's very useful for simulation in a tool like DTM. It's also very useful for your SCADA engineers. They won't have to ask you, hey, what is this GGIO? They won't need a separate spreadsheet. It would just be obvious once they begin to learn the semantics of 62850 and the data structure. Lastly, if you can, utilize the substation section. The substation section, as we talked about during our SEL webinar, is a section or a part of an SCD file. In that, you can do a lot. As kind of a basic feature, you could describe the topology of your substation. So describe the different pieces of bus bar, where they connect, where your breakers are, where they're connected to, and you could lay out a rough single line. This can be utilized by tools to create a single line automatically later on down the line. It can also be used for the specification stage that we'll talk about in greater detail in our next webinar. And is very useful when you're creating an ASD, FSD, and SSD. Additionally, when you're grouping data in a tool like the Data Miner and Test Suite Pro, if you've assigned different logical nodes to be part of different parts of your substation when you were designing that single line, if you kind of associated them based on their application or based on where they lay in your physical topology of your substation, you can group them accordingly, and that can be very useful for finding data. So with that, we come to the end, and I'll talk a little bit about some of the conclusions, some of the things that I hope you guys were able to take away from today. The first is that shift left testing, or testing earlier on in your engineering process, is very useful and very helpful, and leads to a smoother and easier commissioning, saving you time and money, because these errors are easier to correct the earlier you find them. And that 62850 includes tools that enable this. Both unit level testing and system level testing are important, and they are a crucial part of creating a reliable system. Virtual isolation is something that is not fringe. It is well tested and well defined and very powerful, and allows you to do safe and realistic testing that is not disruptive to your system in a new way. And then finally, designing to be tested. If you're thinking about testing holistically and you're thinking about it from the beginning, then it will make testing and validation much easier once you come to those later stages. When you combine all of these things together, it makes for a very powerful ecosystem, and is part of what makes 62850 so unique and so powerful. With that, I want to thank everyone for your time. I don't know if we have any time for questions, but I'll go ahead and turn it back over to Beth to close this out.
Thanks, Jackson. Yes, we are a little bit over time, but we are happy to stay on for a couple more minutes and answer some questions. We've had a lot of good ones come in the last 10 minutes. Let me go ahead and just bring up my presentation real quick. So just to wrap up, if you've already attended a part of our series, you're probably already getting our notifications for the 62050 training. If you want to receive additional notifications on our product releases and other events we're attending, please sign up for our newsletter. It's right on the homepage of our website, and it looks like this. Then you'll just receive our notifications going forward. When you leave the webinar today, you will be presented with a survey. It's only a 5-question survey. We'd love to get your feedback. So please take a minute or two to go ahead and fill that out. We will be posting a recording of this webinar. I'm going to go ahead and put in the chat where you can find the past recordings for the training series, and where this one will get posted in the next couple of weeks as well. And then, of course, if you have any questions or comments, we'd love to hear from you. Please email sales@trianglemicroworks.com. So with that, whoever would like to hang on for a couple more minutes, I will go through some of the questions. So let me just start with the first question here. Christoph, I believe this one is going to be for you. If you do unit testing on one bay, for example, and simulate the missing IEDs and add another commissioner, does a different unit testing at the same time with all other devices that are missing simulated? Would there be interference between the two commissioners testing their unit protection?
If you do that on the final communication network, of course, that will not work, because then you would indeed interfere. We assume that unit testing is typically done to verify the basic behavior before you put it into the system. The key goal is with unit testing, the way we see it, is that you make sure that the basic configuration is correct, because a lot of trouble, sometimes you have something is not correct, configured correctly, and it's easier to find that on a single device than in the whole system. So it's really to make sure everything is configured as you have it in the file, and as such, it needs to be done before you have everything connected. Hope that answered the question.
Okay, thanks, Christoph. Next question, and this might be for you, Jackson, or again, Christoph, feel free to jump in. Will there be a flag set or some kind of indication to the IEC 62050 client, either an RTU, HMI, or gateway, that the signals generated are from the test, or they will look the same as the genuine ones?
Yes, so basically, yes. So if it's a simulated signal, simulated being has the SIM flag set, which is something that would come from a test set or test suite pro, then yes, I mean the SIM flag is set, and that would be clearly visible in a testing tool. If you were to open up Wireshark or something like that, you could inspect the packet and see that that flag is there. If it's if we're talking about mode and behavior, where you have the test bit set, basically the same thing is true. If you were to inspect the packet, you would see the quality has test, and that would be reflected in the GUI of any testing tools that we're visualizing or providing a way to visualize that goose message. I hope that answers the question.
Next question, I believe this will be for you, Christoph. Is it possible to set mode at LD level, or only SIM flag can be set at LD level?
Okay, I'm unmuted now. Mode is always set at LD level. So we have the ln0.mode data object where I can set the mode. I also can set it at logical node level. Any data object, any logical node can have a data object mode. That's optional, so it depends if the device supports it or not. But it's definitely done on the logical device or logical node level. It is the SIM flag, the fact that the device is listening to simulate the message. This is always set at the physical device level, at the ID level. That's why I have the SIM object that switches this to SIM in the LPHD, which represents the physical device, whereas the mode we have on each LN0, which represents a logical device. There may be constraints from vendor that will need to be documented, that when you change one logical device mode, all the other one change as well, because they cannot have part of the device in test and other not. That may basically be there. The good way to model that would be to use now hierarchical logical devices and have one top level logical device and only allow the change of the logical mode of the mode on that level, if the device has limitation with that regard.
Okay, thanks, Christoph. Next question for you. Is it best practice to use LGOS in the data set to the 62050 client so that you can see from the client if subscribers and publishers are getting what they need?
It's definitely a good idea to include the information from the LGOS as an example in a report, so that you can have somewhere a tool, either a test tool like we have shown this Test Tree Pro, where we have our LGOS tool that summarizes the statuses. You could have a similar application running on your local HMI of the station, or you could even imagine to report those information forward to the SCADA. Not sure if the SCADA really needs everything, but yes, I think it's a good idea to put those information in a report and have somewhere a visualization of the situation, how your goose messages are subscribed currently in the system.
Next question, this could be for either you or Jackson. Someone is asking for tools recommended for SSD attendance.
You said SSD, what was the last word?
Attendance, like you attended.
Well, I would suggest Helix STS as a top-down system configuration tool or system engineering tool. So with Helix STS, you can create an SSD file or a system specification description before you've picked out any IEDs. You can specify your applications, and then once you have chosen IEDs, you can then I guess instantiate them would be the word, to create your actual SCD file. Then if you wanted to down the line, you could use that same system specification or the smaller applications that are within it, and you could associate them or instantiate them with different IEDs from another vendor or manufacturer if you chose to. So yes, Helix STS would be my recommendation.
Okay. All right, I think the last question, Christoph, this one will be for you. For SAT using 61850, do you normally make functional tests using secondary injections or repeat simulation test with all devices connected, and then another phase using primary injection?
Looks like you're mind guessing. I was just about to answer that question.
I saw that.
I think that at the end of the day, I would say that depends on the philosophy of the utility. But I would assume in most cases, the SAT testing of your protection and control system is done with secondary injection, primary injection, and testing all your CTVTs. That's typically independent, and it's not so easy to handle.
Okay. Well, with that, I'd like to thank everyone again for attending this training session, and be on the lookout for any follow-ups for the Lab Companion exercise, as well as for the schedule for our next training session. Thanks, everyone.